Now that we've seen what symmetry does to individual points, I want to look at a more general idea of symmetry. And that is, how do we find symmetry? How do we determine whether an equation has y-axis, x-axis, or origin symmetry just based on the equation? Is there something we can do on a larger scale so that we don't have to just pick points out individually to do that? Well, there is. There is a way to do that. But there are some very important aspects. First of all, what we're going to be doing is substituting negative variables in for variables and seeing what happens, right? So, for instance, the y-axis, we're going to take any x values and replace them with negative x and see if the y's stay the same. That kind of makes sense. For the x-axis, we're going to replace y's with negative y's and see if the x's change. If they don't, then it has x-axis symmetry. And for origin symmetry, we're going to replace both variables with their opposites and see if anything changes in the equation. Okay, I'll show you details of that in just a moment. But before we do that, there's some preliminary algebra I just want to clarify and make sure you're clear on. First of all, anytime you take a variable, if a variable is squared and you replace it with a negative variable squared, that negative squared is the same as the original variable squared. Okay, so a negative number squared and a positive opposite squared are always going to be the same thing. Okay, so that's true. I don't really need this extra x squared up here. So basically, whether you square a number or its opposite, it doesn't matter. You're always going to get the same result. Okay, now cubing is different. If you were to cube a negative, it's going to be the opposite of the cube, okay? So if you were to take negative 2 and cube it, you get negative 8. 8 is 2 cubed, so you get the negative of the 8, okay? So with cubes, the negative stays, but with squares, the negative goes away. And in fact, that generalizes even further. We could say that a negative raised to any even power will just become, well, will kind of absorb the negative. Sometimes we say it absorbs the negative, it disappears, the negative disappears. With an odd power, the negative stays. All right, so with a negative to an odd power, we say that that's a negative of the individual variable to that power, okay? Okay, so those are our two, exponent situations. But we also have some other things you might see. For instance, absolute values will absorb a negative. The absolute value of a negative x is equal to the absolute value of x. Those two things are exactly the same. The absolute value of a positive and a negative number are always the same positive number, okay? What other things might you see? If you had a sum or a difference, if you had something like x plus 8 and you wanted to replace that with a negative x, it's not equal to negative x plus 8. These things are different, okay? So if you're adding one with a positive, one with a negative, the result will be different, okay? Same with multiplication. If I had, 3x, that's not the same as 3 times negative x, right? Which is negative 3x. So those two things, 3x and negative 3x, are not the same. All right, so there are times where you get things that are not the same, and there are times where you get things that are the same. It just depends on the situation, okay? Okay, so now we have just kind of a basic overview of what happens when you plug a negative variable or the opposite of a variable in for that variable. Let's take a look at these 3 examples that I have set up here. It gives you a different idea. Okay, so what we're going to do is we're going to test for symmetry, each of these 3 different types of symmetry, and you do them one at a time. You can't do them all together. So the first thing I'm going to do is test for y-axis symmetry. All right, so I'm going to test for y-axis symmetry. And to do that, we're going to replace x with negative x in the equation and see if the y stays the same. All right, y has to stay the same there. So we're going to replace x with negative x. All right, so y equals 3x minus 2 becomes 3 times negative x minus 2. Okay, well, simplify a little bit. 3 times negative x is negative 3x. In fact, I just showed you that a moment ago. Negative 3x. And we know that negative 3x is not the same as the original 3x, which means negative 3x minus 2 is different than the original 3x minus 2. Okay? And because this is not the same as the original 3x minus 2, we would say the y value after replacing with the negative x is different than the y value with the original x. Okay, and so if the two values are different, then we would say that this does not have y-axis symmetry. So no y-axis symmetry. Okay, so now we can move on to x-axis symmetry and test that. Well, with x-axis symmetry, we replace the y with a negative y and see if the x's stay the same, or see basically if the equation stays the same after you simplify. Okay, so we can do that. We can take the original y and call it negative y. So negative y equals 3x minus 2. Now what would be nice is if I could solve for y, and if the other side remains exactly the same as the original, then I know I have y-axis, or I'm sorry, x-axis symmetry. And if it doesn't stay the same, then we don't. So here I would divide out both sides by negative 1, which distributes to both terms on the right. And I end up with y equals negative 3x plus 2. Okay, negative 3x plus 2. Well, unfortunately, negative 3x plus 2 is different from 3x minus 2. These two things are not the same. The signs are both different. Okay, it would have to simplify to the exact same thing. Because it's different, this is not equal to 3x minus 2, then we would say there is no x-axis symmetry. Okay, and so now we'll move on, same equation, but now we'll test for origin symmetry. So to do that, I'm going to plug in both negatives. It's going to be, in fact, maybe I'll move this down where I have a little more space to work. I'm going to go with negative y equals 3 times negative x minus 2. Again, if I solve for y, I'm hoping to have the exact same thing pop out as the original. So I'll make this negative y equals negative 3x minus 2. Divide both sides by negative 1. And I'm left with, well, the negatives cancel here. That's 3x. Negatives cancel here, plus 2. Well, we're close. It's 3x plus 2 rather than 3x minus 2. The minus on the 2 is different than the plus on the 2. And so they're going to be different functions. They're going to be shifted off, a bit. So definitely not the same. This is not equal to 3x minus 2, which means, again, there is no origin symmetry. Okay? Most of the time, your linear equations will have no symmetry.